I understand, yeah.
Just
without micro is a problem.
point defects due to
We have to move to the next talk. I'm sorry, but he's in charge of that. So thank you again very much. We come now to the talk, which is not on strontium titanate, but on aluminum oxide and on cation substitution effects in ferroelectric type oxides. Thank you. Please.
Thank you, Chairman. I'm Itoh from Tokyo Institute of Technology. And today, I will talk about copper alumina type oxide, ferroelectricity in copper alumina type oxide, but not alumina. So please remember that. And so this is my collaborators. And the outline of my talk is that first I will introduce the detail of the crystal structure of the copper alumina type oxide. Secondly, the polarization switching mechanism, and third, site preference of cation in copper alumina type oxide. And the main topic today is the chrome substitution in gallium ferrite films. And this gallium ferrite, sometimes gallium ferrite, people call gallium ferrite type. But the same structure with copper alumina type structure. And also we have carried out the XS and the XMCD measurement for this material. And finally, we have observed the nanodomain structure by the STM. So first, I will explain the copper alumina structure. This is a well-known corundum structure. A corundum structure is made of the cross-packed layers of the oxygen. And inside the octahedral site, the cation can occupy. And the sequence of the cross-packed layers of the oxygen is AB. And in the case of the similar structure is gamma alumina type structure, defect spinel. And in the case of this, the cross-packed layer of oxygen sequence is ABC. And inside the tetrahedral site and octahedral site, cation can occupy like this. And also I will show you the copper alumina type structure. And this material, this is a mixture of the two material. And the oxygen cross-packed layer sequence is becoming ACAB. And also in this structure, you can recognize the corundum layer and the spinel layer. And alternatively stacking along the C direction of this material. And let's cross look for this material. And there is 4 sites for the cations to occupy, A, B, C, D. And A is tetrahedral site, and B, C, D are octahedral site. And this is a corundum layer and spinel layer and corundum layer. Spinel, corundum, spinel, and corundum layer. And if we look at cation arrangement inside the spinel layer, you can see the linear chain of the tetrahedral. And also you can see the linear chain of the octahedra of the B side cation. Also, you can see the if you look at the corundum layer, you can see the double zigzag chain of the octahedral chain like this. And this is complicated. So sometimes people say that this kappa alumina type has a gallium ferrite type or epsilon ferrite type structure. But all are the same. All three. These three have the same structure. And the most important point that the ferro along the C direction, and this material has polarization, electric polarization. And along the A direction, the magnetic easy access exists in this structure. And previously, by Professor Steffler, they have calculated the polarization switching mechanism for gallium ferrite with a kappa alumina structure. And the most important point is that when the electric field is applied, the change of the coordination change occurs along the C direction. For example, the original tetrahedron and octahedron turn into octahedron and tetrahedron. And this is the most important issue of this model. And this is based on the intermediate phase of PNNA. And if you use this intermediate phase, and the activation energy reaches at 0.5 electron volt per formula unit. And maybe this is very large compared to the conventional type of ferroelectric material of barium titanate and lead titanate. And very large compared to that one. So we have re-examined the polarization switching mechanism by the calculation. And in this model, the intermediate phase of during the polarization switching, the PBCN. And the most important point is that in the spinel layer, you can see the coordination exchange between tetrahedra and octahedra. And ordinarily, this site used to be a tetrahedron, but finally, this site turned to octahedron. And this is the A-axis view. And if we look at from the, along the B-axis, it is very easy to understand the mechanism. And in this model, when the electric field is applied, the corundum layer doesn't change their shape, but they shift each other like this. So after the shifting, shearing, the spinel layer changes their coordination from tetrahedra to octahedra, or from octahedra to tetrahedra. And I will just show you the result of the polarization of kappa alumina type structure for alumina, kappa alumina type alumina, and kappa alumina type iron oxide. And the polarization value is 21 to 26. And the most important point is that polarization switching energy is comparable to that of the perovskite, as I mentioned before. So in this material, this material is very complicated because cation position there are 4 cation positions, A, B, C, D. And the smaller cation, trivalent cation can be obtained, can be contained in this structure. And the largest ion is indium, and the smallest one is aluminum. And this material has site preference. And so we have, today I will talk about gallium iron oxide. And we chose chromium substitution because according to the crystal field theory, the chromium cannot take coordination of 4. So maybe if we substitute chromium for gallium, maybe chromium is expected to take to be accommodated in the octahedral site. And according to the previous neutron diffraction data for the nanopowders, and the chromium ion can enter into C and D and C sites in the octahedral site in the corundum layer. And to prepare the single crystalline film, we have used the PLD technique. And all the films were deposited on the strontium titanate 111. This is just an explanation. And this is experimental data for the magnetization and polarization. And this is so this material shows ferroelectricity, ferrimagnetism and ferroelectricity. But today I will skip the magnetism of this material. And the polarization, let's look at the polarization of this material. This is a gallium ferrite, and partially substituted gallium ferrite, and 50% substituted gallium ferrite by chromium, and at room temperature. And these material shows a ferroelectricity like this, and also, but the leakage becoming large with the increase of the chromium content. So we have measured simultaneously. We have measured the PAND and the polarization by the PAND technique. So anyway, although the leakage current increases with the increase in chromium content, and these three materials show the ferroelectricity. And the valency of the coordination was checked by the XAS and the XMCD spectra. And this is the XMCD XAS spectra for this material. And this spectra shows the valency of the ion is 3. And also the XMCD spectra shows that this material, this is a spectra for the gallium ferrite. And this spectra shows that when the chromium is substituted for gallium, the peak for the tetrahedra increases. So it means that chromium, when the chromium is substituted for this material, the kappa ion in the octahedral site is expelled and from the octahedral site, and ion can occupy the tetrahedral site. And this is a summary of the chromium substitution. And we can see that no change was observed in the polarization and the coercive field. So maybe, and let's compare with other system. And this is the previous work on the for this material. And these all material shows ferroelectricity, but the polarization value is small compared to the theoretical value. And this is about 10% of the theoretical value. And so to confirm the origin of discrepancy between the theoretical value and the experimental value, we have checked by the STM observation. And this is a cross-sectional view of the by the STM. And so this is we can see in this system you can see the three kinds of domains and on the STO111 face. And also, this is a plan view of the thin film domains. And there we can observe the three kinds of domains with these directions. And also the average domain width is 12 nanometers. So the reason why this is just an estimation, but if the domain exists like this, with the three variants, and when the electric field is applied, the motion of these variants collide. So maybe this is the reason for the decrease in the experimental value of the polarization So now let's conclude my talk today. Is that we have carried out chrome substitution for this for gallium ferrite, and compared with and the ferroelectricity was observed in this material, and we have compared with the other system in the polarization, and also the similar smaller polarization value was observed in all the systems. So we are now estimating that this is due to the nano-domain structure. And we are now preparing to confirm this origin. We are now preparing the complete single crystalline film on single crystal, and to measure to check the theoretical value of the 20 to 25 microcoulomb per square centimeters. Thank you for attention.
Thank you very much, and I see there are a few questions.
Very nice talk. You had no time to discuss magnetic properties, but definitely you studied something. Can you comment magnetoelectric coupling in this system?
Because we should measure the M effect, for example. But in the case of there is a domains inside. Exactly, we cannot determine the ME coupling value of this battery, but only the simple measurement was carried out and by the the sign of the I cannot. Sign of the
Thank you.